Why does simple harmonic motion look exactly like a trig wave? Because it is one. Every spring, every pendulum, and every vibration is a circle in disguise. And what I'm going to cover today is what determines the period of simple harmonic motion, why the motion looks like sine, and how to express different values like position, velocity, acceleration using trig functions and time. As a bonus, we can also have a deeper look at intuition and graphs. First, what's a period? The period is given by t, and it's how long one oscillation takes. So for example, one full bounce of a spring or one back and forth swing of a pendulum. The more mass, the slower this oscillation is because there's more inertia. So the heavier the slower. Pretty straightforward. The stiffer your spring or your cord, so the larger this value, the spring stiffness constant, is, the faster your oscillation because it snaps back harder. And here's something surprising about amplitude, which is the maximum height of your wave, your spring, whatever. The amplitude, it doesn't affect period. The timing of the oscillation, it doesn't care about amplitude. If the bounce is really big compared to a bounce that's really small, assuming it's the same spring, it's the same mass and everything, the bounce takes the same amount of time. This surprises people, but it's good to know. I'm going to talk about frequency. Frequency pops up a lot in things like harmonics, pitch. Frequency is 1 over time, which is the inverse of the period, 1 over frequency. It simply means how many times does your object bounce up and down in this amount of time. So there's another formula for this, and there's a big derivation behind it, so I'm not going to go into where it came from. I'll just chuck it on the free cheat sheet in the description. It's a pretty important formula. It's 1 over 2 pi times root k over m. This is a frequency formula we're going to use in problem solving later on. The unit that you measure frequency in is hertz, cycles per second. And it's used when you want to look for how often, not how long, something takes to vibrate. Now, why is simple harmonic motion sinusoidal? Big word. But why does it look like a trig wave? Where does trig come from? I did actually make a full 90-minute masterclass on the channel that you can go check out if your trig is behind or weak. But picture this. Imagine a mass moving in a circle. It's traveling in this circular path. Now just watch the shadow of it on the wall behind it. The shadow as it travels in a circle. The vertical motion is what's changing here. And as it varies, if you graph it at every single second, so you rise, then you lower, then you go down, then back up. Look at that. It's a sine wave. It comes from the unit circle of trigonometry. And if you understand the unit circle, a lot of physics becomes intuitive, like vectors, this kind of stuff. So the math of bouncing is the math of circular motion flattened into a line. This is why you'll see equations like this for physics topics. This is where sine comes into play. So that's why simple harmonic motion looks like waves. And when you track something bouncing up and down, you can use the trig functions to describe it and solve for specific values. Here are some equations that you don't need to understand, but I just want to show you them. For position, there's an equation that looks like this. Cosine graphs look like that, and you can use cosine to find position. For velocity, there's a formula like this, and it uses sine to find velocity. And for acceleration, there's also one. It uses cosine again. All of these things are trig functions, and all of trig functions can be graphed as waves. Let's go through an example problem. Your phone has a vibration motor. So every phone has a vibration motor. So when someone calls you, it starts vibrating. The vibration motor makes it oscillate up and down. The internal mechanism is 0.05 kilograms. And it oscillates at a frequency of 20 hertz. Assume it moves like a spring mass system, so simple harmonic motion. We're going to solve for two values. First, we're going to estimate the stiffness. And two, if we added a new piece of 0.30 kilograms. What's the new frequency of the vibration motor? First, use the formula from the cheat sheet that we talked about earlier for frequency. Why do we use this formula? Because we're looking for stiffness, and it matches up what we know. We know mass. We're not going to use Hooke's law for this because we don't know the force or the displacement. You have to select the right formula that links what you know and what you need. Rearrange for K with your excellent math skills. Having good math skills makes physics very, very easy. It immensely lightens the load. Once you rearrange it, your equation looks like this. Solving for K. Plug in your values. The only thing we have to plug in, by the way, is the frequency, 20 Hertz, and the mass, 0.05. The answer for the stiffness constant of your vibration motor, 789.6 Newton meters. How about problem B? The new frequency in Hertz when you add weight to it. So when your thing is heavier. Like we talked about earlier, the heavier something is, the slower it oscillates. The more mass, the slower the vibration because of inertia. The new mass of our thing is 0.080 kilograms. And here's a proportional equation. The frequency is inversely proportional to the root of the mass. This is something people found. This comes from that formula from earlier. So it's inversely proportional to the root of the mass. What does that mean? It means it scales with the mass in this way. This means that our new frequency is equal to the original frequency, or the old frequency of 20 Hertz, multiplied by the old mass, 0.5, divided by the new mass. It's equal to 20 times 0.05 over 0.08. It gives you 15.82 Hertz, your new frequency. It's slower than 20 Hertz. It's slower because we added a lot of mass to it. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.